Hey you guys, I'm back. I just had a enormous chicken tender and one of those Hostess cherry pies that are kind of like a cherry pie pocket with all that sugar syrup that gets poured over the pie crust, if you will. And so that was a great little break that I had there to talk about the standardized practice test. I'm back again now to hopefully finish up the standardized practice test, unless we get into a discussion that lasts way long, and maybe we'll need a third video to talk about and complete the standardized practice test. But I'm hoping that we can get her done without too much difficulty. Okay, so you're recording your answers on the answer sheet. You're writing down things that I say that are just remarkable, right? What does remarkable mean? That means you ought to write it down because it's remarkable. Okay, so are you ready for number 9 on page 547 of our ICP textbooks, right? Integrated Chemistry and Physics. Awesome sauce. Page 547, problem number 9 reads as follows. Define the general properties of metals that make them useful and versatile materials. Okay, so we're talking about the metals. They're on the left side of the periodic table. We know some things about metals because of what we have learned about the various groups of metals by reading this chapter, right? So here's metals. I'm just going to go off the top of my head. So you guys should write down all of these things, and feel free to write down anything I don't write down that you know is true about metals, okay? So, right off the bat, they conduct electricity. And why is that? Because they're willing to give up their electron or electrons in their outer energy level. So they conduct electricity, generally speaking. Aluminum and copper are great elements to use to conduct electricity because their electrons are very free, and they are also ductile. You can pull them into a wire. And so in addition to being able to be ductile, they also are free-flowing with electrons, and you can surround them with an insulator, a plastic insulator, that doesn't give up electrons because all the electrons are in covalent bonds. And so that they're good for conducting electricity, generally speaking. Metals are. Also, generally speaking about metals, is they're ductile. Can be drawn into a wire. Now that's hard for mercury at room temperature. Mercury is a liquid, right? But generally speaking, metal elements are ductile. What about malleable? There's a difference between malleable and ductile. Malleable is when you can hit it with a hammer and it'll flatten out without breaking apart. Okay, so malleable is true. Ductile is true, generally speaking. Malleable is true, generally speaking. Obviously, if you hit liquid mercury with a hammer, you're going to get a splash. And, you know, there's other specific elements, like hydrogen is not really considered a metal. It's more considered a non-metal, even though they put hydrogen in the group 1 alkali metals. Group 2, alkali earth metals. Then you have the transition metals. And you have the lactinide and actinide series metals, transition elements. Maybe but they're considered metals because they want to give up electrons more than they want to receive electrons. Okay? And I'm sure there's a few exceptions to all that. Conduct electricity, ductile, malleable. What else about a metal gives up electrons. I better put an R there. Electrons to get full outer energy level. Okay? That's another thing. Metals. There are the groups. Metal groups are the alkali metals, the alkali earth metals, and the transition elements. Okay? So groups. Can you think of anything else, generally speaking, about metals? If you can, feel free to write it down. Okay, so that was number 9, right? Number 9. Define the general properties of metals that make them useful and versatile materials. Okay? Use the electron configurations of sodium and potassium to explain why they do not naturally occur in elemental form. Okay? Use the electron configurations of sodium. So here's the electron configuration of sodium. This is number 10. Sodium has a single electron in its outer energy level. So we want to write that down so that we can use the electron configuration of sodium and potassium. So this is sodium. And we've got potassium. Here's potassium. It has one electron in its outer energy level. This is called potassium. Capital K on the periodic table. Both of these elements are in group 1, or the alkali metal group. Okay? Use the electron configurations of sodium and potassium to explain why they do not naturally occur in elemental form. All right. These elements have only one electron in the outer energy level, and they really, really, really want a full outer energy level. So that they really want to get rid of that electron. They want to get rid of that electron so bad. I mean, these are angry. These elements are angry trying to get rid of that electron. All right? And their neighbor, the element, any neighborly element will take that electron from them. Right? Chlorine, sodium chloride, potassium chloride, right? There's all kinds of ionic compounds that form with sodium and potassium. We're going to talk a lot more about that in the next chapter, where we start to talk about chemical reactions. So here we are. We've got these things. So having only one electron, they are highly reactive. Even with water. If I drop, by the way, there's a picture of sodium being dropped in water. Back here in your chapter, I want to draw I remembered while I was traveling to and from that this picture that we looked at showed sodium reacting with water. It's on page 520. So if you could turn to page 520 and look at this picture to see it more clearly, that might make sense. But you'll see right here in this beaker, the caption for that picture is, alkali metals are very reactive. For example, the vigorous reaction between potassium and water, oh, that's potassium. That's not sodium, that's potassium. Between potassium and water releases enough thermal energy to ignite the hydrogen gas that forms. I think last time I was talking about the fact that the water molecule turns into, basically the OH gets grabbed. I said something like, but I was wrong about that. I'm remembering, so I want to correct that. So this is sodium metal plus H2O. Chemical reaction goes like this. It makes H2 and O2. Right? I'm sorry, it makes OH and sodium plus. This is OH minus and sodium plus in the water. Okay? This is in excess water. So it makes that H2 plus OH minus plus Na plus. Now let's balance this reaction. Is that balanced? Not quite. Okay? So what we have to do here is, let's try 2 on the H2O. That means I need 4 over here. And if I put a 2 there, it's done. Now this is a balanced equation. Okay? There's the same number of sodiums on both sides. There's the same number of hydrogens on both sides. There's 4 hydrogens here. There's 2 there and 2 here. And then there's 2 oxygens and there's 2 oxygens. So there's the same number of oxygens. I hope you guys could see that chemical reaction while I was just doing all that pointing. Sorry if you couldn't. Okay? So this is actually the chemical reaction of what happens when you drop sodium into a beaker of water. Now, and the thermal energy that's given off because of that reaction is ignites the hydrogen with the air in the room. So the hydrogen catches fire. That's why you have flame showing there, because it's so hot that the hydrogen then, with heat given off during the reaction, becomes reacts with oxygen in the air. So you got H2 plus O2 goes back to H2O. Okay? And so you have to put a 2 here and a 2 here to balance that equation. So there's actually 2 chemical reactions happening in this thing. These sparks flying off are chunks of metal that are going off and combusting with the atmosphere. Okay, and this right here is flame, because the H2 that's given off with the reaction with water is immediately combusting. It's so hot. Okay, this is an explosive reaction. You never want to put a great big chunk of potassium in water and be near it. It's amazingly reactive, very, very exothermic. Okay, so I don't think you needed to write all that down to answer this question. I think you needed to write this down to answer question number 10. Okay? So let's go on to question number 11. Question number 11. Define the term allotrope and identify these allotropes of carbon. Okay? So we've got this picture of allotropes of carbon. All right? That was nice of them to give us a picture. That really helps us to define the word allotrope. You know, the fact that they're giving us an example of carbon allotropes right here. Okay? So don't miss that. That's a great gift, as a matter of fact, if you ever, when you're taking a test. So define the term allotrope and identify these allotropes of carbon. All right, so what is the term allotrope? What does that mean? I bet you've got it in your outline somewhere. At least I hope you do. You might look that up and convince yourself that you know what the definition of an allotrope is. But let's say, let's write down the definition of an allotrope in our own words. Number 11. Okay, allotrope. All right, it is a molecule of an element that is different from other molecular formations of that element. Okay? So an allotrope is, and you see, what you see here are two different allotropes of carbon. There's actually a third allotrope of carbon, and that's a diamond. I don't think a diamond is shown here in this diagram. What you see here in this diagram, these three, this is half of the diagram, and this is the other half of the diagram, okay? This is what is considered graphite. You see, graphite forms long carbon sheets, and so they can slide with one another. That's why graphite is a good lubricant in skateboards and other things, all right? Because graphite can slide. The substance actually moves and changes its shape because of friction, okay? And this, I think, is, that might be a diamond. This might be diamond configuration of carbon. Let's look back in the book at another picture and make sure that I'm not lying to you. It was in the very end of the, the very end of the chapter where they talked about allotropes. Okay, look. Great. This is great video evidence. So graphite does this, okay, has 3 layers of carbon, and diamonds are shaped like this. The carbon is in a matrix, and in this shape, this unit repeats itself over and over again, and that unit makes a real pretty diamond when you have this repeating itself over and over again. It's pure carbon, but it's a different shape. Obviously, graphite is black, and diamonds are not. They're clear. Light passes through them, and it's very pretty when light passes through them. Okay? So, and then there was one more shape for carbon that's created. They call this the soccer ball shape, or a buckyball. Okay? So there's actually, carbon has 3 allotropes, not just 2. All right, so an allotrope definition, generally speaking, is a molecule of an element that is different from other molecular formations of that element. Okay? And that's question number 11. And we talked about allotropes of carbon. Let's talk about one other allotrope. Okay? Oxygen. So oxygen, O2, is a diatomic molecule a lot of the time in our atmosphere. O2 is a diatomic molecule. You've seen me draw this molecule before. oxygen double bonded with its remaining outer level electrons like this. Okay? When I draw a dashed line between two elemental symbols, that means there's two electrons being shared between the two elements. There's element symbols that are on the board. So there's actually two electrons associated with this oxygen and two electrons associated with that oxygen. And they are bonded, is what those dashes mean on these kinds of electron dot diagrams. Okay? So this is one symbol for oxygen. This is another symbol for oxygen. Okay? So that's one way oxygen forms as a diatomic molecule. Now, oxygen will also become ozone. When you hit oxygen molecules with electromagnetic radiation high in our atmosphere, oxygen becomes ozone. So what you end up with is a triad of oxygen elements that are singly bonded to one another, and there's still these other electrons hanging out. Okay, in the outer energy level. So what this is one of the electrons associated with this oxygen. This is one of the electrons associated with that oxygen, and it's bonded in a triangular formation. It's called ozone. You've heard of ozone. Ozone is high in our atmosphere. Ozone gets created because oxygen diatomic molecules collide in the upper atmosphere, and the electrons of those oxygen diatomic molecules are in an excited state because they're up there absorbing ultraviolet radiation from the sun, protecting us from ultraviolet radiation from the sun. So that ultraviolet radiation puts the electrons of an oxygen molecule into an excited state, and then when two oxygen molecules combine, you can get three of them to create ozone, and then actually the chemical reaction, this chemical reaction of O2 to O3, I'll put it right here for you. I'll put it right here. O2 in the presence of UV radiation becomes O3. So let's look at this. You need three oxygen atoms to collide in the presence of UV radiation to get two ozone molecules. Three oxygen molecules to make two ozone molecules. Do you understand what I just said there, everybody? Okay? So that's actually three. So the concentration of oxygen in our atmosphere is very important to be able to have three diatomic oxygen molecules come together and collide in our upper atmosphere in the presence of ultraviolet radiation to make two ozone molecules. Okay? Now, there you have it. This happens. And it's reversible. This reaction is completely reversible. Two ozone molecules might come together and collide under the right conditions and become three diatomic oxygen molecules. Two ozone molecules, bang, hit each other, and they become, and so that's reversible. It takes energy to make three oxygen diatomic molecules into two ozone molecules, and there's energy released when two ozone molecules collide and become three oxygen molecules. A little bit of energy release. So you get UV radiation in the presence of all that, and it becomes, I believe when the ozone goes back to oxygen, you actually don't get UV radiation given off, you get infrared radiation given off, which is not as harmful, much lower, more radiation beams of infrared, but not as powerful as UV radiation. Same amount of energy, one way versus the other, but different forms of energy. Okay, I love you guys. I hope you followed that. And so anyway, ozone to oxygen. These are allotropes. These two different molecular formations of oxygen element are allotropes. Hope that helped. All right. So define the term allotrope and identify these allotropes of carbon. That was question number 11. Compare the structures of these carbon allotropes and relate the structures to the properties of these materials. Well, we were talking about the properties of these materials already. We talked about graphite and sliding, or maybe sloughing off a layer is possible. And so there's a lubricant quality to graphite. But diamonds, no, there's no lubricating property there. Diamonds cut, and they cut with the sharp edge that gets created by that diamond molecule. Okay? So a diamond will cut, graphite will reduce friction. Okay, describe some unique properties of hydrogen. Describe some unique properties of hydrogen. That's just the question, number 13. Question number 13, unique properties of hydrogen. Let's describe them. That was we did number 12 already, talking about allotropes, and number 12. Let's go on to number 13. So that's number 13, I guess. Number 13, again, says, describe some unique properties of hydrogen. All right, unique properties of hydrogen. Okay, hydrogen. So what do we know about hydrogen? It sits atop the alkali metals group. I'm pointing at the periodic table over there on that side of the room. You can look at your own periodic table, find hydrogen. It is the upper leftmost element, hydrogen, capital H. Okay, hydrogen. It does not exist all by itself in nature. Okay? If you drew an electron diagram, it would look like that. Do you see why it does not exist in nature? Because it looks like that? It will become a diatom, a diatomic molecule, where H with an electron and another electron. So no matter what, this element hits, whether it's oxygen or carbon or nitrogen or chlorine or whatever neighbor this hydrogen element runs into, this hydrogen element is going to react with it. It doesn't matter if any nonmetal, this hydrogen metal, if you will, it's really not a metal, it's unique. So it's sort of a metal. We're going to write down sort of a metal as a unique attribute of hydrogen. Okay? It is so reactive that it does not exist in nature. I can't walk up to and pick up a lump of hydrogen. I can't even find, if I have a glass jar that's full of hydrogen, let's say this 2-liter bottle was full of pure hydrogen. I would not have hydrogen all by itself, individual elements of hydrogen. I would have this. I would have individual diatomic molecules of hydrogen if I had nothing but hydrogen in this bottle. Okay? It does not exist by itself in nature. Okay? So that's kind of unique about hydrogen. So reactive, it does not exist in nature. Okay? What else? Some other unique properties of hydrogen. It's a gas all by itself. This is a gas. Right? diatomic molecule. To be exactly right. Okay, so it is the smallest. It has only one proton. It is the smallest atomic number. Of 1, right? Has 1 electron. Does that make sense? It has 1 electron. It has 1 proton at its center. Okay? What else? That's enough. Let's move on. Okay? So we described some unique properties of hydrogen right there on the board. Okay? What halogens are commonly obtained from seawater? What are their uses? So what halogens are commonly extracted from seawater? Now, water dissolves a nonmetal and a halogen because the halogen wants an electron so much that it steals the electron. It doesn't share the electron with another element, another nonmetal. So, for example, you can have, this is number 14, you can have calcium chloride. Okay, so that's calcium that has 2 electrons. It's in the alkali earth metal column, or group 2, and this is chlorine, which has 6, 7. This is the chlorine electron. I'm going to turn these to X's, and I'm going to put another chlorine over here, and it has a dot, and then 6 other electrons in its outer energy level. Okay? So calcium chloride, CaCl2, calcium chloride. All right? And this will dissolve in water. So calcium chloride in water becomes Ca2 plus 2Cl minus ions. You have 3 ions that form in water. Calcium chloride, 2 chlorine ions with a -1 charge each, because they've taken this electron from calcium, and the water molecules all oriented so that electromagnetic, that becomes possible in water. The bipolar H2O molecule surrounds this in such a way that the chlorine floats away, and the chlorine floats away with both of those electrons, and the calcium becomes charged with 2 plus, and the calcium ion has a lot of water molecules with the oxygen, with the oxygen part of the water molecule pointed towards the calcium ion, and that each chlorine ion floats away with a glob of water molecules around it, where the 2 hydrogen atoms are all pointed toward the chlorine ion. Big glob of water molecules that make that ion stable. Okay? That's why things dissolve in water. Ionic bonds dissolve in water. For example, calcium chloride. Now, question number 14 again is, what halogens are commonly obtained from seawater? Well, chlorine, fluorine, right? All of them. Chlorine, fluorine, bromine, iodine, or iodine, and I can't remember what AT is again, but there's AT. Atnium, I think, or something like that. Okay? So chlorine, fluorine, bromine, iodine, and atnium. All of the halogens can be found in seawater, and they can be purified out of seawater. That's the answer to question number 14. What halogen can't be commonly obtained from seawater? and seawater. Okay? What are their uses? So, what are the uses of chlorine gas and fluorine gas and bromine gas and iron? So, these things are used in chemical industry to react with other things. For example, carbon tetrachloride. You want to make carbon tetrachloride. You have 4 chlorine atoms attached to 1 carbon atom. Carbon tetrachloride. Okay? For example. And that's a really good solvent because it has the same center of positive and negative charge here in this configuration. The center of both the positive and the negative charge is the same place in that molecule. Carbon tetrachloride. Okay? And so that's good for dissolving things that wouldn't dissolve in water. Carbon tetrachloride is a great solvent for things that don't dissolve in water because they have an aversion to water molecules, and so you can, it's a great solvent. You can make a lot of pharmaceuticals using carbon tetrachloride. Now, carbon tetrachloride is not good for you, so you're just using it in the process to make a pharmaceutical chemical molecule for, that will dissolve in carbon tetrachloride but not dissolve in water. So you can actually separate the molecule that you want out of the aqueous solution or water solution, and you can actually move it over to carbon tetrachloride, and then you can evaporate the carbon tetrachloride away in another step in the process, and then all you have left is the purified molecule that you want, for example. Okay, so you use these elements to make molecules that you need in chemical processing. Did I write that down? Was that number 15? What halogens are commonly obtained from seawater, and what are their uses? Well, so all of these halogens are commonly purified from seawater, and they are used to make desired chemicals. All right? I mean, I don't know how to say it better. Used to make desired chemicals. What are their uses? To make desired chemicals. Right? Okay, number 15. Recent Federal Drug Administration statements advise limiting consumption of tuna and salmon. Which transition metal is the source of the problem? Mercury. Explain why this element poses a potential risk. Mercury is a transition element that contaminates your blood. It takes up the site of the hemoglobin, where the oxygen molecule and the carbon dioxide molecule exchange places, right? In your lungs, the oxygen jumps onto the hemoglobin and the carbon dioxide comes off and out of your body. Out in your muscles, the oxygen molecule comes off of the hemoglobin and the carbon dioxide molecule jumps on because of the concentrations there out in your muscle, and then that hemoglobin comes back to your lungs, etc., etc., etc. Now that site, that's actually got an iron element, an iron atom sitting on that hemoglobin site that is where the carbon dioxide and the oxygen exchange, okay? And what happens is mercury will attach there on the iron site. And now it never comes off. O2 can't knock it off. Carbon dioxide can't knock it off. So now your red blood cell becomes useless. That's one of the toxic effects of mercury. Another toxic effect of mercury is that it can go into your nervous system cells and it stays there, and it interferes with the activity of the nervous system. And so, you know, you start doing this. When you get too much mercury in your nervous system, and it never leaves, never leaves. You understand? Because if that cell where it's in and causing you difficulty it dies and gets replaced by another neuron, well, the mercury didn't leave your body. It just moved over into that other neuron. So anyway, mercury's not a good thing to consume, not a good thing to touch. It's a hazardous chemical. And so recent FDA statements advise limiting consumption of tuna and salmon because mercury poisoning of the lakes where the tuna and the salmon come from exists. So the tuna and the salmon end up with mercury in their bodies, and then when we eat their muscle mass because it tastes good, we are consuming mercury that never goes away. And so they recommend strongly that you not eat too much tuna and salmon that has been contaminated by toxic mercury element. Okay? So number 15, the answer is mercury. And there were two reasons I gave. There were two reasons I gave for the toxicity of it. So mercury, I'm going to write mercury. I'm going to write mercury. Okay? And the two toxic effects are diminished respiratory function and interference with neurons. Okay, and if you have too much interference with neurons, you start doing this. I'm sorry. I'm not making fun of anybody that has mercury poisoning. I'm just saying, right? Okay, number 16. Identify the type of bond shown in that picture above. Use the figure below to answer question 16. Number 16. It happens to be question number 16, and the figure is above. Isn't that nice? So you got all these sodium plus ions. Now they're ions. They're not just sodium atoms there in the matrix. They're sodium ions. So identify the type of bond shown. Okay. Well, I guess you'd have to call this a metallic bond. Describe the properties of a material with these bonds. This is a very positively charged sodium metal. There are no sodiums that are neutral. All the sodium ions are missing an electron. This is an incredibly charged chunk of sodium metal. I mean, I've been talking about charges in my physics class, talking about electricity in physics class, and the fact that electricity is the movement of electrons. The electrons that are missing in this diagram scare me, because this is a very positively charged sodium metal chunk. Okay, you see that? They're all missing an electron. So identify the type of bond shown. Well, that's a metallic bond. And describe the properties of a material with these bonds. Well, metals. And this is charged. I don't know what else to say. So number 16 is, it's a metallic bond. Let's see, I'll come over here for number 16. We're going to write metallic bonding, and the properties of the material with these bonds are, it's a metal, right? It's highly reactive. And I would say also highly charged. Highly charged. Positively. It's not negatively charged. It's positively charged. Okay? Can you guys see that answer well? I think so. 16, right? Yeah. There you go. That's what I wrote down. 2 little answers. Okay? Number 17. Compare the 2 types of bonds that nonmetals can form. Okay? 2 types of bonds that nonmetals can form. All right? There's covalent and there are ionic bonds that nonmetals can form. Is it okay if I erase number 1 here? I think it is. I'm going to do it. All right. So number 17, compare the 2 types of bond that nonmetals can form. Okay? Well, here's ionic and there's covalent bonds that nonmetals can form with metals or nonmetals. Okay? An ionic bond is where, well, number 1, it dissolves in water, and it also, the halogen, does it say halogen here? 2 types of bonds, oh, nonmetal. The nonmetal will steal an electron from a metal. Okay? Now, covalent bond. This happens when the nonmetal shares an electron with a metal or nonmetal. The nonmetal will steal an electron from a metal. That forms an ionic bond. So when you have a chemical reaction between elements that are at the left of the periodic table, these alkali metals, these alkali earth metals, and these transition metals, when you have a chemical reaction on the left from an element that's on the left side of the periodic table, and the other chemical that's reacting with it is not the noble metals, they don't react with anything, but these nonmetals, okay, you're going to have either ionic bonds or covalent bonds. All right? Does that make sense? They're going to react. The easier it is for the element of the metal to give up an electron, which those first 2 columns, it's real easy for them to give up an electron. With anything over there on the nonmetals on the right side of the periodic table, you're going to get an ionic bond. But when you're, like, say, for example, calcium and oxygen, they're not, calcium's in the second group, and oxygen is needing 2 electrons to fill its outer energy level, you're going to see more of a covalent bond there, okay? Calcium oxide doesn't dissolve in water very much, almost insoluble in water, okay? All right, So we got that done, number 17. Number 18, explain why fluorine is a very reactive and why neon is very unreactive. All right, so you'll notice fluorine and neon are right next to each other on the periodic table. Look it up on the periodic table. You'll see that fluorine and neon are right next to each other here on the periodic table. This one is very highly reactive. It needs one more electron. Fluorine needs one more electron to get to a full outer energy level, and neon already has a full outer energy level. Okay? So neon doesn't want more electrons to make a full outer energy level, and so neon is a noble gas. It doesn't react with anything. No other element on the periodic table. Neon does not react with it because it has a full outer energy level. It doesn't want an electron. It doesn't want to give up an electron. But fluorine wants an electron really, really bad. As a matter of fact, you will not find fluorine element in nature unbound with another element. You don't walk up and find a chunk of fluorine anywhere. Okay? Neon is a gas, and you can find neon gas in our atmosphere, individual elements of neon gas. But you will not find fluorine in nature all by itself. It reacts with anything it touches. Okay? So what was that question? Explain why fluorine is very reactive and why neon is very unreactive. Number 18. We'll do that right here. I'm going to try to put that into words now, what I just got done explaining to you. All right, fluorine needs a single electron to have a full outer energy level. And that is way more stable. Having a full outer energy level of electrons is far more stable than having one less electron in the outer energy level. Okay? Mathematically speaking, when fluorine gets an electron from another element, its neighbor, when fluorine gets an electron, it is much in a de-energized state. It's much simpler for it to exist because of the full electron cloud. Okay? So fluorine needs a single electron to have a full outer energy level and less, I'm going to call it chemical potential energy, and lessen its chemical potential energy. Okay? That's why it's reactive. Okay. Fluorine is reactive because it needs a single electron, okay? Now, neon is unreactive because it has a full outer energy level. I'm getting out of the way here in just a second. All right, number 18. Fluorine is reactive because it needs a single electron to have a full outer energy level and lessen its chemical potential energy. Neon is unreactive because it has a full outer energy level. And it does not want, it doesn't want to gain an electron or give up an electron. Okay? That was number 18. Number 19. Why is helium instead of hydrogen used in blimps? Okay? If you guys remember the Hindenburg, you remember the Hindenburg blimp that came from Europe to America and then got struck by lightning, we believe, and started to combust in the with the oxygen in our air. So why is helium used in blimps instead of hydrogen? Because hydrogen will combust with oxygen if it's given a spark, an ignition source. Okay? So hydrogen will combust. It will react with oxygen, right? Whereas helium is inert. You can't make it burn. Helium is inert. It will not react with anything. You hear me? Now, when you talk about helium, it's actually twice as heavy as H2 molecules. A helium atom is twice as heavy as H2 molecules. So it actually requires a great deal more volume to float a blimp than hydrogen does. If you're using hydrogen, you don't need as much volume because it's lighter. Hydrogen is lighter. Okay? Helium is heavier, but that's okay. You still want to use helium if you can afford to. If you can afford to use helium to float a blimp, that'd be the thing to do, because it won't burn up if somebody lights a cigarette. Boom! Sorry for laughing. All right. So that was number 19. Number 20. Explain the importance of organisms that convert nitrogen from its diatomic form into other compounds. Wow. Isn't this an integrated chemistry and physics class? This sounds like a biology question, doesn't it? Number 20. Explain the importance of organisms that convert nitrogen from its diatomic form into other compounds. Okay? So, nitrogen is a gas, right? It's in our atmosphere. 78%, oh, I shouldn't have erased that maybe. Well, this was number 19, and this said hydrogen will combust. Sorry, I started to erase the wrong problem. I should have erased number, let's come over here and erase number 13 and 15, okay? That's been on the board for a long time. 13, 14, and 15 are disappearing now, and we're going to get number 20 done, okay? So, nitrogen, 78% of our atmosphere is nitrogen. And nitrogen does not exist by itself. It's also a diatomic molecule. Nitrogen reacts and shares 3 electrons. Each nitrogen brings 3 electrons to share with the other nitrogen. So this is 6 electrons, and nitrogen only has 2 others. That gives it 8 electrons in its outer energy level. That's why nitrogen does that, okay? So 78% of the atmosphere is nitrogen, N2, or nitrogen triply bonded with another nitrogen element, okay? Now, why is it good that biological organisms convert nitrogen into other things? Like, let's say, ammonia, right? So nitrogen wants to be, when you combine it with hydrogen, you get NH3. Okay, that's ammonia. Okay, and let's balance this equation. Let's put a 2 here and a 3 here. And now this is a balanced equation. There are 2 nitrogen element atoms on each side. There are 6 hydrogen atoms on each side. NH3 looks like this. I'm sorry, that's 4. I was done. That's NH3. Okay? And you get 2 of those. 2 NH3 molecules with 1 nitrogen diatomic molecule from the atmosphere and 3 hydrogen diatomic molecules from a source. Maybe H2O in vitro, in a living organism. Okay? Ammonia is a really good it's a really good fertilizer. As a matter of fact, ammonium nitrate is you get a bag of ammonium nitrate, and it's a really good fertilizer. Okay, and you spread it out in your garden and watch it grow. Shoo! The difference putting nitrogen putting nitrogen down into the earth, giving plants nitrogen at their roots, so that nitrogen can go up into the tree and help reproduce cells and multiply cells and grow leaves and other things. It's very much useful to put nitrogen back down into the earth from the atmosphere. Okay? So the answer to number 20 is: explain the importance of organisms that convert nitrogen from its diatomic form into other compounds. Okay, so we need living organisms to bring nitrogen back into the earth so that plants can grow. Let's write that down. We need organisms to bring nitrogen gas from the atmosphere into the ground, so plants can grow. Okay? Does that make sense, everybody? We need organisms to bring nitrogen gas from the atmosphere into the ground so plants can grow. All right? We need to make nitrogen into a water-soluble molecule. Okay? So that it will go into the ground and feed plants. All right, that was number 20 of our standardized test practice. I am so pleased that we got through that. Now, that was a lot of information, and I know it was a lot of information. I want you to know that that was our Chapter 16 assessment. So you guys write down the answers to questions 1 through 20 by watching these 2 videos that I've put it all in. And be sure to watch that first lecture I wrote as well. I gave it to you probably about over a week, right at a week ago now. And we're done with Chapter 16, and we're moving on to Chapter 17. So why don't I just tell you the Chapter 17 outline will be due next Thursday. And we'll talk some more between now and then. I hope you guys are having a great, great, great day. Let's pray again. Lord, we know that our knowledge of science can be used to glorify you. And we want our knowledge of science to glorify you. Help us not to be afraid of mathematics or science or any area of science. For we can understand how to calculate a death rate for coronavirus, because we know how to do dimensional analysis, and we know that we can divide the number of deaths by the number of people that had coronavirus and get a lethality percentage from that. And there's all kinds of things that we know that we don't even know that we know. But don't let us be fearful of science. Don't allow that to be true in our lives. Make it possible for us to embrace science and scientific knowledge, because the more we learn about science, the more we believe in God's hand doing it all. In your mighty name, Jesus, amen. I love you guys. Take care.